Good afternoon. Today the plan is talking about control flow hazards and branch prediction. So for your quiz one, whatever we say today, end of this module would be what will come in your quiz one. There is a slight chance that we don't finish all the slides today. In that case, a little bit of Tuesday will be also dedicated to kind of finish this. On Tuesday next week, I'm going to also do a full review of all the things that we talked about. So definitely try to attend the Tuesday class as well. We're going to release a homework probably tonight or tomorrow, hopefully, which would be based on things that we discussed this week and things that we discussed last week. And this will be very helpful for your quiz as well. Computer assignment 2 will be based on the lecture today, actually, and some of the things we might say next week. It will be based on branch prediction. It will be released next, probably the weekend after your quiz or the following week. And discussion sessions, definitely go to them. The TAs and LAs have slides for how to do the project. If you have questions about the project, they have dedicated time, you can ask them. Also, next week's Wednesday going to be dedicated fully for just kind of Q&A for you guys. If you have any questions about any of the topics that we discussed so far, next Wednesday is a great time to go to any of these sessions and ask questions. Any logistical questions, anyone? Yes. If you want to, next week is these are optional. You can, if you have questions that you want to answer before the quiz, obviously you want to go on Wednesday one, right? And then this Friday also helps, right? So you can. Yes. For the quiz, you're gonna get a cheat sheet. Yes, I'm gonna have, as I said, a separate post on Campus Wire about like the size and stuff like that. Okay. Last week, this was the design that we mainly focused on. We essentially talked about two important things. We talked about the hazard detection unit and how we insert the bubble and how we are actually kind of stall the processor by kind of disabling the two registers. And then we also talked about forwarding and how we kind of like decide what to forward in order to make sure that the data that we are reading is the correct data. And the plan was basically stopping, kind of eliminating the need for stalling the processor. Yes, sir.
Well, this, so putting back, if there were that question next week, do we, will this part be given, will this drawing be given or given?
Questions about drawings, usually we're gonna give you the drawing and you can build on top of it, yes. Yeah. Yeah, try to, if you like, focus, if you want to be super focused on your quiz, what I would do is trying to understand how this works, okay? We said that, okay, in addition to the data hazards that we talked about, there's also two other hazards, the structural hazards and control hazards. A structural hazard is when of these units are busy and you want to kind of like move instructions forward, and then one of the units are busy, so you cannot like do that. As a result, you need to basically stall a processor. So that essentially the data path design that we went after is not going to have a structural hazard, but just keep in mind that could exist. So our focus today is going to be on branches and how we resolve the issue of branches. We're going to first talk about what is the control flow data hazard. Control flow hazard. And then we're going to talk about various ways that we're going to fix this issue. So we're going to start with like simple things, and we're going to go very advanced into like dynamic branch predictions. And again, the goal here is we want to improve the performance of the processor such that if a control flow hazard exists, we can detect it right in time, and we can actually fix it and without any penalty to the performance. Okay, so first of all, let's see what is the problem. I showed this picture before. Essentially, the problem with branches is that in our instruction memory, generally in our memory, we always assume that the memory is linear, right? And when we have situation like if then else's, what will happen is that you have a code block here and another code block here, but you either run this code block or this code block, right? So what will happen is that regardless of how you structure this in your memory, you either put C first and then B next, or B first and then C next. Whichever you do, you would need to run one part and then skip over the other part, or skip over one part and then continue, right? So there needs to be some movement in your instruction memory. When we were talking about the ISA, we talked about how we actually do this by changing the PC. But if you look at this problem from the perspective of pipelining, when you're jumping over instructions, you're going to run into an issue called control hazards. So what is a control hazard? Control hazard definition is that when the flow of instruction is not known or expected, then you need to somehow kind of stop the pipelining and kind of like revert and then kind of fix this. Because when we are doing the pipelining, the assumption is that we are always doing the next PC, next PC, next PC, which in our design is PC plus 4. So this way we can actually kind of feed the pipeline over and over again. But if you need to somehow skip some instructions, then I need a mechanism to detect that, okay, now I no longer need to do PC plus 4. I need to actually jump somewhere else in the program. So there needs to be a lot of activities going on here to fix that issue, okay? And if you think about this and kind of compare this with the single cycle, control flow hazard didn't exist in the single cycle. The reason for that was in single cycle, you let one instruction to fully finish, and then you go to the next instruction, right? So once the instruction is fully finished, you already computed your PC, you already computed your PC and plus offset. You know the condition of your branch, whether it's true or not. So you already know what would be your next instruction, and then you can update the PC before going to the next cycle, and as a result, you're never going to run into a control flow hazard. But in a pipelining, that's not the case, right? So in a pipelining, let's say, for example, I have fetch, decode, execution, memory, and write back. So these are the 5 stages that I have. And let's say I have one instruction that is an add, another instruction that is a sub, and then a branch instruction, and then maybe an XOR instruction, right? So the way it would work for me, it would work is that I put, fetch. Actually, let me remove these. So the first instruction goes to fetch. These are kind of like our cycles, okay? So the first instruction goes to fetch. In the next cycle, the instruction goes to decode. Now we can bring in the sub instruction. In the next cycle, this one goes to the execute. The sub goes to the decode, and now I can bring my fetch instruction, right? So far, so good. This one goes to the memory. Let's say for now, there is no dependency, or if there is dependency, there are forwarding. So there's no issue of that. So I can move this to the execution stage. I can move my branch instruction also to the decode stage. And now it's the time to decide, right? So we need to decide whether or not we want to fetch the XOR here, or whether we need to kind of skip and then fetch some other instruction, whatever, wherever the branch is, right? So if in regular systems, if there is no branch, you just continue XOR and then the next instruction and next instruction. But what if that in fact you need to take the jump and jump over the memory, right? This is a problem that we refer to as a control flow hazard. In cases that you are jumping over, then you shouldn't have fetched this instruction. So we need to fix this issue. And as I said, in single cycle, this problem does not exist because you essentially kind of do all the fetch, decode, execute, memory, and write back in one cycle, and then do the next cycle again, the whole thing. So you already know this. Yes. Say it again. Last one. Uh-huh. So the question is why, what's wrong with fetching XOR? So if I fetch XOR here, then the fetch next cycle will go to the decode and execute and memory and write back. So, and then I'm not even supposed to run this instruction. I'm supposed to jump over this instruction, right? So going back to this if then else, right? Let's say, for example, I get to this instruction x equal to y, and the condition is true. So I need to actually run this block. I shouldn't run this block, right? If I run this block, I'm just running different instructions that I'm not even supposed to run this, right? Well, we're gonna talk about what we're gonna do to fix this, right? So what we need to do is, first of all, we need to understand this is a problem, right? So we see an XOR and we kind of need to make different, we need to make different decisions. Should we, for example, whenever we see a branch, we can maybe stall the processor and let the branch finish it and then continue. But maybe we can do other things. Maybe we can do better things to fix this, okay? All right, so yeah, so that's actually a good connection to what we want to do. The first solution that comes to mind is why don't we stall the processor, right? So whenever we see a branch, we don't fetch the next instruction. We wait for the branch to quote unquote resolve. When the branch is resolved, then we can move on to the next instruction, okay? It's a good solution. This would be a vanilla solution. It would require some stalling in the processor, and we're gonna answer how many cycles we're gonna stall. But keep in mind that we always really want to achieve better and more performance. So stalling is an option, but we always try to minimize the amount of stalls. Okay, but for now, let's assume that we just want to stall. So first question: how many cycles do we need to stall to resolve a branch? Yes, sir. One cycle?
Yeah.
Okay. Anyone else wants to? Any? 2, 3? Yeah. Until it reaches the execution. Okay, so 2 cycles. Okay. Do we have a 3? You can, we can say, yeah, I'm trying to say, what's the worst case? Give me that. You just need you need to know the outcome of the branch. So the question is, how many cycles do I need to wait to know the outcome of the branch? Yeah. Okay, 2 cycles. You are also saying 2 cycles because that's when we know the PC plus offset. Okay. All right. So let me actually so in order to answer these questions, this is what you need to know. This is kind of referred to as 3 W's for a branch instruction. So essentially, in order to know the outcome of the branch, you need to know 3 things. One is that you need to know that this current instruction is a branch instruction, right? So regular instructions, you don't have control flow problem at all, right? So control flow problem happens when you have a branch instruction. So first thing that you need to know is that you need to understand this is a branch instruction. Second thing that you need to know is where this branch is going to, right? So if I want to take this branch, what is the destination address? That is, what is the PC plus offset? And the third thing that you need to know is that whether or not this branch is going to be taken or not, right? So for example, for something like JAL and JALR, once you know that this is a branch, like a control flow instruction, you know that this will be taken. But for example, for something like BEQ or BNE and less than and greater than and so on and so forth, you also need to check some conditions. So in some cases, you take the branch. In some cases, you don't take the branch. Okay? So let's see actually in our design which cycle each of these things happen. Okay? The first one is we need to know when this instruction is a branch instruction. When do we know that? We know that during the decode, right? So we know that when we are reading the opcode, we can say that, oh, this is a branch instruction because the opcode matches with the branch instruction, right? So in our design, the answer to the first question is that we know immediately in the decode stage that this is a branch instruction. The second question is, where does the branch go? And for this, we need PC plus offset. We need the results of PC plus offset. If you look at this design that we have here, the PC plus offset thing is actually shown here, right? So this is your PC plus offset, right? The offset coming from here and PC coming from here. So you have your PC plus offset kind of at the end of the execution unit, right? And lastly, whether or not you're taking this branch is going to be this gate here, this branch gate, which is basically taking this control signal that this was, if you remember, was this control signal called branch. And this is basically coming from this 0, okay? So this would be known at the memory stage, kind of somewhere in the middle of the memory stage, okay? Some people will ask that, why don't we move this gate here so we could actually also like move this gate here, and this way I kind of save one cycle. You could do that, but that increases the critical path of your execution stage. The reason that we move it here is because the critical path of the execution stage is very important. It's long already, so I don't want to extend it any further. That's why I moved the gate to the memory stage. So just keep that in mind. Later, you're going to see that we're going to actually change this logic a little bit. So for now, we're going to put it in the memory stage. Later on, we're going to move it back. Okay. All right. So kind of summary. When do we know that the instruction is a branch instruction? Is at the end of the decode stage, when the controller basically knows that this is a branch instruction. Where does this branch go is PC plus offset, which kind of we know it at the end of the execution stage, in other words, beginning of the memory stage. And when do we know that whether the branch is taken or not is somewhere in the middle of the memory stage? By the end of the memory stage, we know for sure that whether this branch is taken or not. Yes. Yeah, so for knowing whether or not your branch is taken, this is what you need to compute, right? So this signal here is basically telling you whether your branch condition is true or not. One of them is coming from the 0. One of them is a control signal that is coming from the control, which was that branch instruction. Yes, this is the AND gates. Yes, this is the AND. Yeah, it happens during the memory stage. Yeah, it has nothing to do with memory, but it happens during the memory stage. Because essentially, when I say memory stage, I mean happens between these two registers, right? These are your pipeline registers. Timeline-wise, happens when things are in the memory stage are happening.
So unrelated with the zero flags, obviously it's only gonna write that it's only gonna branch when like the AND actually works with the branch signal lock. So I know the zero flag is important, but like for other instructions, like we just ignore the zero flag, or like what is it set to add or something.
Yeah, so the question is somewhat irrelevant to the branch, but the question is what happens in the zero flag for other instructions? For other instructions, this is just an arithmetic operation. So basically what it does is that, for example, if we only support branch equal for now, what it does is RS2 minus RS1. So if for any instruction your RS2 minus RS1 happens to be 0, this becomes 0, okay? But keep in mind that this basically goes into this AND gate, and the other part of this AND gate is coming from the controller, from the branch control signal. And that branch control signal is always 0 unless this is a branch instruction. So this part of this AND gate is always 0. So it doesn't matter what is the value of the other part of the AND gate.
Yeah. Other operation. Like adding zero flag.
It becomes, so if you're adding 2 and it becomes 0 again, doesn't matter, right? So, I mean, it's just a wire that is not connected to anywhere. So there's this notion of don't care, okay? So you don't care whether this value is 0 or 1 because it has nothing to do with the rest of the operation. Yeah, so these are the pipeline stages. This is your instruction fetch, IF or F. This is instruction decode, ID or D. Sometimes we show it as ID, sometimes we show it as D. This is your execution that we sometimes show it as E or EX. This is your memory stage, M or MEM. And this is your write back stage that we typically show it as WB. So remember that we are pipelining our register. These are the control signals. So these boxes are essentially you're passing through the control signals. That eventually, so WB is that the control signal eventually reach to the write back stage. But these are all what we discussed in the Tuesday. So I recommend to, if you don't understand it fully, go back to that and then you'll understand it better. Okay, so going back to our branch, is there any other questions? All right, so going back to the branch, we know these 3 questions at this time. So if I actually look at the max of this, I know the outcome of the branch kind of at the end of the memory state, right? Because I need all 3 information to make a decision, okay? So going back to our design, okay, if I have a branch equal, for example, X12, X0 label, what will happen is that branch starts from the instruction memory in the fetch state. It goes to the branch equal. Here, I cannot fetch this instruction because it's still, I don't know the outcome of the branch. Here, I only know that this is a branch instruction. So I know the first W, but I don't know the answer of the other 2 Ws, okay? Then I move forward. At this point, I have the value of the 0. So I have there. So I know first question here, second question here, and then I know whether or not branch is taking the jump here. So this would be basically the question the third question, okay? So again, I cannot, since I know this as kind of like the middle to end of this cycle, I cannot fetch the instruction here still because I need to update my PC to be able to read the next value. So actually, when I can like basically read the instruction is when at this cycle here, right? So I can only like, update my read my next instruction after 3 cycles. So in this cycle, I cannot fetch anything. In this cycle, I cannot fetch anything. In this cycle, I cannot fetch anything. I can start fetching things starting here, okay? You might, and then this is regardless of whether your branch is taken or not taken, right? You don't know until you actually check the condition. So whenever you see a branch, you stall for 3 cycles, you read it from this. Either you read the next instruction here, or you take the branch and do it the PC plus ops. Yes?
So when you say you can't fetch, are you fetching all 3 instructions or all 4 instructions at the same time?
No. So these are just examples. So you're not fetching all 4 instructions at the same time. I'm saying that these are, think about this as just the cycles. Cycle 1, cycle 2, cycle 3. I'm not fetching any of them. I'm just installing the processor.
Oh, so you're
You're not doing anything, right? So you stall at this moment. Whenever I see that my instruction is a branch instruction here, I'm going to stall the processor. Okay? Yeah. So forwarding would be here. Like again, you know it at this point, so there's not much you can forward. That's why you actually kind of like, the beginning of the next cycle, you already know the number. Yes. Always in that order, is it like which one we know when? You have a question? So the question is about like, we know the first question in the decode, and then second question in the execution, and third question in the memory. Is that always the case? For the design that we have, yes, right? So how did I come up with those cycles is based on this design, right? if I change this design, if I move the circuitry, for example, for PC plus offset here, then I know the answer to the second question at this cycle, right? So it's just the design of the data path that leads to these answers. Yes. So the question is when you are stalling, how exactly do we stall? Do we need to like insert the no-ops? Just keep in mind that we are stalling the processor at the fetch state, so we don't need to even like feed anything forward. We just let the branch to continue. Yes, yeah, PC literally stops, yeah. So we're not gonna implement this. That's why I'm not showing the actual implementation. We're gonna optimize this further and then show you the final implementation. But yeah, if I wanted to implement this, then I would stall the PC. If need be, I can always insert the bubbles as well, or not. All right, so let's see how bad this is. Branch instruction actually are quite common in most of the applications. On average, in like standard benchmarks, 20% of the instructions are some form of a branch or a jump. Those are control flow instructions, okay? And if I'm stalling 3 cycles for each time that I see a branch, you can actually compute your CPI to see what would be the average CPI of this. But 1 out of 5, you're stalling your processor 3 times. Okay, so your performance is not going to be great. Okay, so the question is how we can make this better, right? So obviously stalling is an option, but it's not an option that we like. For really low-end processors, this could be good enough. But for more high-end processors, you want to do more. Okay, so how do we do it? This is the idea of what we call branch prediction. Starting today, you're going to see that this is kind of like one of the very important tricks that we're going to use a lot in computer architecture, that an event is happening. And this could be a branch event, or it could be many other events that we're going to discuss later. One option is that we need to wait and decide what is the outcome of that event, which translates into stalling the processor and losing performance. The second option is making some form of a guess. If that guess is a good guess, that is accurate most of the time, then we may not need to stall the processor at all. Okay, so this is kind of like a very handy trick that you're going to see a lot in computer architecture. In fact, this is what we call generally as a speculation. Okay, speculation means that whenever either your compiler or your hardware processors guesses an outcome of an activity, an event, it could be an instruction, it could be dependence removal, it could be many things that, again, as I said, once we talked about other advanced features of a computer, CPU and microarchitecture, you're going to see this a lot. But whenever we make some guesses and make some action based on that guesses, it's called speculation. And when we are running things in that speculative state, we call it speculative execution. Okay, so a branch is one example of that. Okay, for branch, speculation is somewhat easy because essentially a branch has 2 outcomes. Either the branch is taken or the branch is not taken, right? So my speculation is kind of a binary decision. Whenever I see a branch, I make a decision. For example, I say that, okay, the branch is going to be not taken. For now, let's actually have a very dumb guessing mechanism, which is whenever I see any control flow instruction, a JAL or a branch, I'm going to predict it not taken, and this is a stat. Okay, so let's see actually what will happen. So for a branch like this, remember I told you that, okay, the branch goes here and then goes here and so on and so forth. And then up to this point, I need to stall the processor. And only at this point, I can basically fetch the first instruction, okay? But imagine that whenever I see a branch, I predict not taken. So what I can do is that whenever I see a branch, say, oh, okay, there's a branch here. This branch is going to be not taken. This is my speculation. So I can actually fetch I1 here. The branch goes to the second cycle, I1 comes here, I2 goes here, and so on and so forth. So in fact, if you predict not taken, and this branch is in fact not taken, you're not going to lose any performance. You don't need to stall your processor at all, right? Which is nice in terms of the performance. So let me give you some stats. Remember I told you that 20% of instructions are control flow. There's some form of a branch. Out of that 20%, 50% of them 50% of forward branches are taken. Okay, so branches could be forward or backward. What does that mean? It means that if I have a branch or a gel, it could either jump to the positive addresses or may jump into negative addresses, right? So sometimes you jump back. If your offset is negative, you jump back. If your offset is positive, you jump forward. Okay, these ones that is jump forward we call forward branches. This ones that are you jump backward, we call backward branches. Okay, so interestingly, out of all the forward branches, 50% of them are taken. Out of backward branches, 90% of them are actually taken. Backward branches, think about it as like for loop while loops, right? In a for loop, majority of your jumps are actually true, right? So like for example, for I equal to 1, I less than 100, 99% of the time, 99% of the time of the iteration, this is a taken branch, okay? So actually, if you're plugging the numbers, you will see that 86% of the time, this is basically 80% of non-branches and 30% accuracy on that 20% branches. You are good to go. That, you know, either this instruction is not a branch at all, and so you don't need to bother, and you just do PC+4, or this branch is indeed this instruction is indeed a branch. Well, at least 30% of the time you are correct with your prediction, and then you just move forward with your branch. Okay. You might also wonder that why don't we then do not taken branches, because this will obviously shows that if we actually predict taken, we would be significantly more accurate, right? Because right now we are predicting not taken, but for example here it basically says that only 10% of the time you're correct. We will do that later, but not taken is much easier for us to do. Why? Because for not taken, I already know the next address, and the next address is PC+4. For taken, I need to compute PC plus offset, which is a little bit more difficult. Later, I'm going to show you how we predict taken, but for now, we're going to just do the simplest thing, which is not taken. That make sense? Any questions? Yes.
So if we start doing the not taken, and then figure out what that's was taken, but we have already changed the registers, how we can change it back.
Yeah, this is so what if we actually make an incorrect decision, right? So what if we predict taken and it's not taken, or we predict not taken and it's a taken? So we need to take care of that. So I'm going to talk about that. There was another question? It's the same question? All right. Any other questions? Okay, so let's talk about that. So speculation in general, there is the downside of a speculation, and that is that you make a wrong guess, right? So for example, for branch, whatever you do, you can never have 100% accuracy, unfortunately. Even if you're 99% accurate, there is 1% chance that you make an incorrect decision. And this incorrect decision actually leads into correctness issues. So it's not like, yeah, okay, we make a wrong decision, whatever. You actually need to fix it, because if you actually take the wrong path, then the outcome of your program is going to be wrong, and then the whole thing is broken down. So we need a mechanism to fix that. So let's talk about that mechanism first. Then I'm going to show you how to improve the branch prediction accuracy. Okay? In order to fix this issue, if you are making a wrong decision, what we need to do is that we need a mechanism to flush the pipeline. Basically, what we are doing is that we are bringing so we make a guess and we're bringing some instructions, and we realize that, we made a wrong decision. We need to somehow flush those instructions outside the pipeline, okay? How do we actually implement this flushing? The flushing is very similar to when we are inserting bubble. Essentially, what we do when we are flushing is that when we realize that we made a mistake, we're going to immediately substitute those instructions with a bubble. Okay? So not only we had those muxes in the decode stage, so this was the mux that you had during the decode stage. Now we are introducing additional muxes in the way of your execution stage, your memory stage, and your write back stage. And what it does is basically replacing the control signals of that instruction with zeros. Because I can let the garbage continue. I can add garbage with garbage. I can multiply garbage with garbage. I can read things from the memory, garbage reading, all that. As long as I don't write anything to my register file or to my memory, and I don't change my PC, then I'm good to go. Okay? So the trick that we're going to use is that we're going to let things go. Sometimes I'm going to talk about when we realize that we made a mistake. But if we catch that mistake, what we do is that we say that, okay, all of the control signals, everything's zero. So we don't write to a register file. We don't write to memory. We don't change the PC. If we don't do any of these three things, we are okay. We just do extra activities. So we lose some power, but who cares? Yeah. They don't write to. So the question is, what happens? They write to an operand. So when we control signals are zero, like if your read write is zero, your mem write is zero, your PC source is zero, you don't write to any of them. Okay. Actually, we would. I mean, we're gonna talk about how many cycles you're gonna miss, but essentially, yeah, it could be like one cycle, it could be even less than. It could be zero in some cases. Yeah.
At what cycle we already taken?
At what cycle we know it's taken. So we're gonna go back to that. It would be memory. Like remember the 3W questions? Same story. So you know it during the memory stage. But I'm gonna show you the breakdown. Yes.
Where once realize that it wrong finish, then it's too late, already written something that where does that not?
So the question is, would that be a scenario where when you realize it's too late, you have already written? You have to design it such that it doesn't happen, right? So this is the job of the designer to make sure that their data path controller is designed such that the latest worst case scenario that you detect the branch is happening, nothing has been written at that point, which is okay because essentially, as I'm going to show you, you know things in the memory stage, you've written back things in the write back stage. So you have one cycle of fixes. Yes. Yes, all the flushing signals, the question is, where are these coming from? Yes, they're all coming from essentially, I mean, we're going to later talk about it. So essentially, your branch misprediction is also part of your hazard detection because your hazard is data hazard and control flow hazard. So yeah, the controller basically issued that signal. Hey. So basically here what happens, right? So I told you that basically what we do is that we assume that the branch is not taken. So we do I1 branch equal branch I1 here, I2 here, branch equal I1 here, I2 here, I3 here. At this point, we will know exactly whether or not your branch is taken, where it's going to, and whether this is a branch. So if we decide that we need to flush things out, we'll let the BEQ to continue. But instead of like moving I1, I move no op here. I move no op here. I move no op here. And here I'm actually fetching the correct instruction, whatever that is. Okay. So that's what I'm going to do. So I'm replacing I1, I2, and I3 with 3 no ops, and then let the no ops continue. Yes.
So instead of stalling, we have in case.
Yes. Instead of stalling, we make a prediction. We let the instruction continue, and then if we make a mistake, we flush. Yeah. Yeah. And then again, if you remember, common case faster, right? That's the golden rule in computer architecture. If the common case is optimized, then you're going to get benefit. that if you are correct more than the times that you're incorrect, then you're gonna get overall performance benefit. Yes. So the question is that if we are taking the branch, where are we going? That depends on the label, right? The label might be far away. At this point, you know exactly what your label is, right? So at this point, I can actually correct, fetch the right instruction. It could be I4, it could be anywhere else. That specific fetch would be the correct instruction, whatever PC plus offset is pointing to. Yeah, you had a question?
That was my question, but then, so the no-ops go through, and then like you still have like whatever was in instruction memory, right? But then when you take in I4, it just overwrites like,
The I4 never fetched, right? So at this point, PC is already updated to PC plus offset. So you don't never fetch I4.
right, my question is like, the no-op,
The no-ops continue in the pipeline, yeah. But no-op is not an issue. Yeah. So are we flushing those? Are we installing the processor? So no, again, so that's the beauty of the no-op, right? So for the no-op, you can just let the no-ops continue. You don't need to install anything. You just let the no-op. So part of your pipeline will be filled with no-op, and then you can actually fetch the correct instruction at that site, right? But if you think about this, is that essentially you are still losing 3 cycles, because for 3 cycles you're not using anything useful. You're not stalling, but you're also not you're not doing anything useful either, right? Yeah. Question is, how many cycles do we flush and why we are doing these things? Again, goes back to the 3W question, that we know the outcome of the branch during the memory stage. So during the memory stage, we know whether or not we need to flush. Okay, so if we know sooner, we would have flushed sooner, right? So that's actually one of the optimizations that we're going to make. That if we know the outcome of the branch somehow as fast as possible, I can flush less. But for now, the design that we have was the outcome of the branch. The condition for the zero AND with branch was known during the memory stage. Okay? Yeah. Yeah, so the question is, why don't we know the outcome of the branch earlier? And we're gonna do that. Just wait. Yes.
but this is strictly better than like all this stuff.
Yes, so this is a strictly better by how much, do you know? So it used to be 80%. Now it's 86%. So we are improving by 6%. Still, in 14% of the time, we are losing performance. We just do extra activity, but at least that 14% doesn't lead into correctness issues, right? We just feed no ops during that 14% of it. Yeah.
Each hit one different part of like the pipeline.
Yes.
And then as soon as we hit the, no below, sorry. Okay, that was, but as soon as we hit the memory stage of that first branch.
Yes.
Then we have to place there's 3 things that you, so we put no ops in all 3 of those.
Yes. So essentially timeline wise, what you said I'm going to repeat is that at this point, I will realize that I made a mistake, right? This branch was taken, but I predicted not taken. And I need to flush these guys outside the pipeline. So what do? At this point, I kind of notify the controller. The controller will issue these signals. And what we're going to do is that once the next positive edge of the clock comes, I pass through zeros. I don't pass through the actual instructions. Okay? Perfect. So this is actually called branch miss penalty. Penalty means that the cycles that we are supposed to do something useful, but we are not. Okay? So essentially, we are in this design that we have, our branch miss penalty is 3 cycles. Again, we are not introducing correctness issues. We fixed that issue, but still our branch miss penalty is 3 cycles. Okay, and our branch accuracy, detection accuracy is 86%, right? Because for all the non-branch instruction, we predict not taken, and that's great because 80% of the time that's true. For taken branches, on average, we are only accurate by 30%. So together, it's only 86% accuracy and 3 cycle of penalty. Yes.
For these architecture, will it be smart and for engineer to write the instructions and have take data?
That's a great point. Mostly not taken, right? So yeah. So if your design, if you have a branch predictor that always predict not taken, if you can write the code such that majority of your time your branches are not taken, you're gonna get the performance benefit. Yeah. In fact, you later on, when we do the dynamic branch predictor, you will see that there are compiler support to kind of tell the branch that this branch is likely to be taken versus not taken, and so on. So you can actually do these tricks. All right. So any questions up to this point? Okay. So rest of this lecture, we're going to try to make this better and better and better. Hopefully we can get to 100% with 0. So I want to reduce 2 things. I want to reduce my miss penalty, and I want to increase my branch prediction accuracy. If I can do either or both of these things, immediately I'm going to get performance benefit, right? Your CA2 will be also based on branch prediction. We're going to ask you to design a branch predictor that is very accurate. Okay, and you're going to play different things to make the branch predictor accurate. I'm going to talk a little bit about like what is the state of the art, but you're going to actually try to see if you can improve that. Okay, so what are the things we can do? There are 2 things we can do. We can make the accuracy and prediction better. We can also try to reduce the miss penalty, because if I have my crappy branch predictor, but at least I know that I made a mistake as soon as possible, that's also good, right? So let's actually focus on that first, and then we're going to talk about how to make the branch accuracy better. Okay, so how can we make the branch miss penalty less? We can do this by basically resolving the branch sooner. Going back to the question that we had, remember that the 3 W's, right? We know whether this is a branch or not, where it goes, and whether it's taken or not, right? Sorry, whether it's taken or not. So when we know it's a branch, we know it during the decode stage, right? Where it's going, we know it during the ALU stage, during the execution stage. Whether it's taken or not, we know it during the memory stage. So if I somehow can move these guys to the decode stage as well, I can only pay penalty of 1 cycle. So if I can resolve everything during the decode stage, this is the fastest that we can do, right? If I know everything during the decode stage, at least the penalty will be reduced from 3 cycles to only 1 cycle. Okay, so that's what we're trying to do. You had a question there, Mark? No. Where that 6% improvement came from? So 20% of the instructions are branches. Out of that branches, 50% of forward branches are taken. That means that 50% of the time we are correct, 50% of the time we're not correct. From the backward branches, 90% of the backward branches are taken, which means that 10% of the time we are correct. Plug in the numbers, assume that equal distribution of forward and backward. Plug in the numbers, you get to the 86%. Okay? All right, so we want to move everything to the decode stage. Okay, so we know the when answer, but we don't have the where and whether answer. Okay, so what do we need to do? So we need to do two things. We need to move the computation of next PC, which is PC plus offset, move that to the decode stage. We also need to resolve the condition that whether or not, for example, RS1 is equal to RS2 also in the decode stage. Okay, so this is what we're going to do. So we're gonna basically take whatever was here, it used to be here, I'm gonna move it here, right? So I basically have my immediate generator here. I can also move the adder to here. So I have the PC plus offset during the decode stage. Now used to be here, there is a zero signal here. So I had my ALU. Now, since I need to kind of like know the answer of the question of whether or not these two registers are equal to each other or any other. So for now, I'm just supporting branch equal. But if I want to do less than and all that, I basically needs to have somewhat a mini ALU here that can give me the answer of that question as well. And from here, I will create another control signal. I'm not showing you here, but this would be my zero, okay? So the zero comes out from here. So what I'm doing is that I move the comparison for the zero flag during the decode stage. I also move the PC plus offset during the decode stage. So all three things now happens during the decode stage. The design is significantly more complicated. This critical path is much longer, but as long as it's less than the ALU operation and memory operation, we are good to go. Okay, and what does this give us? This helps us with reducing the miss penalty from 3 cycles to only 1 cycle. So I know the only thing that I need to flush would be basically the instruction in the. So during the decode, I will realize that, oh, this is a branch. I will just flush the very next instruction and I'm good to go. Okay? There are a bunch of questions. Yes. Yeah, it did increase the critical path, but not by much. Okay? So it's still, as long as this design is balanced, then you're good to go. Yeah.
And I just made like two, like one mini ALU, but let's see if that matter.
Yes. So I had this adder before as well, right? So this adder I'm not introducing, I'm just moving it. The thing that I'm introducing extra is here. So I'm adding more things to my processor, and now you can see how from 10 billion transistors we move to like 50 billion and hundreds of billions of transistors because we keep adding features to our processors. Here's one of the examples. I'm kind of adding a new kind of semi-ALU into my design just to be able to resolve my branch soon. Okay? Yeah.
So G here is a equal sign, the stuff, it's basically an extra ALU you will add to our system, and immediately out of the register you will know the result, whether it will jump.
Yes, so this is kind of like a mini ALU that you can assume, yes. And immediately after that, you will know the flag, whatever flag it is. So for this case, it's just branch equal, but it could be all, if you want to add support for other type of branches, you can add support there as well. Yeah. Yeah, well, I mean, yes, you would probably then, if I need to support more, then there will be an input to this guy as well of like, oh, this is less than, or this is greater than, and all that. Yes. Would it be the same command from the control? It could be the same command from the control, yeah. So assuming that in your original design, for example, we ask you to support branch not equal, right? There you probably have some tricks to kind of like change the ALU operation, or maybe you looked at func3, func7. There's different ways you can do that. Same tricks applies here. Yeah. Adding another box where? I'm adding another AL. So mux, I'm not adding so we add muxes here to just flushing, right? So these are the muxes that we added to do the flushing. Here, I'm not adding another additional muxes. I'm just moving the ALU. I'm just moving this adder here. I'm adding these two red things, right? So this one and this one I'm adding. One last question. It does increase the critical path for this stage, right? It does increase the critical path for the decode stage. But remember, the clock cycle was decided as the max of all the stages, right? If I already have some leeways in the decode stage, I increase decode stage by 10%, 20%. But if 10% is still less than the data memory, you're good.
The other stages are memory access and ALU already stage up.
Is already memory ALU operation, if it's like floating point or memory mainly, is already much more than the 110% of your decode. Yes. Okay, one last question. Good question. Does this introduce data hazards? Do you think it does? It does, right? Actually, yes. So this will introduce data hazard. How? The data hazard basically comes that, remember that here we had the forwarding, right? But now I have, if for example, there is an instruction here that change RS1, then I don't have support for forwarding during the decode stage, right? I had support for forwarding during the execution stage. So there are two options that we need to do. Either if we detect that there is a raw data hazard, I stall, so I can no longer use this trick. So I go back to miss penalty of 2 or 3 cycles. Or there is another, like you can do another crazy thing, which is bring the forwarding logic to your decode stage as well. For now, you can safely assume that either we don't have the raw data hazard, but if we do, we stall for 1 cycle. Because if we stall for 1 cycle, then I have forwarding logic here. Then I can make a decision during the execution stage. Okay. So as I said, the only thing that I need to basically do now is that I need to flush the fetch. So my miss penalty from 3 cycles reduced to 1 cycle. Okay. All right, so this is basically what will happen. So I get my branch equal. I take my I1. Now what is changing is that at this point, I realize that I made a mistake. All I need to do is that I insert the bubble and flush I1 out. And then at this stage, the BEQ goes here. And I can fetch the right instruction here, whatever that right instruction is. Okay? And last thing, as I said, is do I have a raw data hazard? Yes, I do have a raw data hazard because essentially, as I said, if RS1 or RS2 is being written by a younger instruction, an older instruction, then this condition checking is not correct, right? I need to do the forwarding again. And remember, forwarding was not done here. It was doing here because I assumed that my ALU was here, and now I'm introducing a new ALU here. So I have 2 options. One is I support the forwarding the same way I did support forwarding for the ALU stage here. So I need to introduce new muxes. I need to change the forwarding logic and all that. So that's one way of doing that. The second way of doing that is that just the hazard detection unit, if it detects that this is indeed a data hazard, it will stall the processor for 1 cycle. So the miss penalty becomes 2 cycles. Okay, so we already have the technique to stall the processor. We stall the processor for 1 cycle, then we actually make the decision. Yeah. Yeah. So for example, like say I have this, right? So let's say the sequence was like this. I had add x12, x11, and x10, right? And then I have branch equal x12, x0, and label, right? So what will happen is that I can only run this instruction when the registers are updated, because if I'm doing it during the decode, I can only do it when the instructions are updated. The way that we fixed that previously was we forwarded during the ALU stage, right? But since now I'm making decision during the decode stage, I don't have that forwarding logic. So either I stall the processor 1 cycle that it goes through the ALU and then do the forwarding like the way that we did in the past, or we need to somehow move the forwarding logic here and support the forwarding during the decode stage. Both of them are valid options and both of them have been implemented. Okay? Okay, so let's have a quick break. We'll come back and talk about more advanced branch prediction. All right, so we reduce our miss penalty. So far, what we did was reducing our miss penalty from 3 cycles to 1 cycle. For that, I need to make a lot of changes to my data path. I introduced a lot of things, including a new kind of ALU. I also moved my adder, and I increased a little bit my critical path of my my decode stage. But these things worth it because it reduces the cycles, the miss penalty cycles of a branch from 3 cycles to only 1 cycle. Okay, so and again, as you can see, these are all trade-offs. So it's not like, oh, we always have to do this or we always have to do the other. Whether or not you should like add this extra complexity to your design is a function of the specification. Like, what is the application that you are using? What is the amount of power and area and cost that you're willing to invest and spend on this design? For a high-end processors, absolutely. Anything that gives you more performance, you would do it. For a low-end processor, no. You don't want to add additional ALU to your design because it will increase the power consumption. It will increase the area size and things like that. So it's not like you always do this or the other. It really depends on the class of CPUs that you're talking about, okay? So just keep that in mind. Another thing is that generally the discussion that we had both the last lecture and this lecture is very layered. So we start with some simple design and we keep adding features and features. My suggestion to you, for you to understand these things, like, you need to iterate a few times over this design to understand it. On Tuesday, we're going to do that as well. So I'm going to actually kind of, again, start from the top and go to the bottom. But now that you have the full picture, you will understand this a little bit better. But it requires a few times of repeating this process of like learning each one of these one by one. And hopefully it'll kind of gels together and you understand it better. Okay? That's why you have the recording, so you can actually watch or rewatch certain part of the lecture, both today's and the Tuesday lecture. Okay. Last thing about, we kind of like discussed it, but what is the role of the compiler in this? Compilers can do multiple things. First of all, it can increase or decrease the chance of certain outcomes, right? So for example, if you have a branch that is always not taken, I can actually write my code such that the not taken is more likely than taken. Another thing that we do is that if we are doing this resolving during the decode stage, okay, since I'm flushing 1 cycle, so I'm basically, my miss penalty is on 1 cycle. This is what usually refers to as a delay slot. Essentially, there is a branch, and the next instruction after the branch is very likely to be flushed, right? So assuming that your branch predictor is not so accurate, if I have a design like this, the instruction immediately after the branch is going to be flushed, right? So what I can, this is basically called a delay slot. This is a slot that you're probably not going to get anything useful out of it, right? So what the compiler can do is, if my branch is like this, so let's say, for example, I have a sequence of instruction that looks like this, and my branch jumps to here, and then afterwards these two converge, okay? So I have a sequence like this, that at this point, my if then else branch converge into the same point, okay? So what you can see is that this instruction, regardless of whether or not your branch is taken, this instruction is going to be executed, right? So what the compiler can do is that it moves this instruction to here, okay? So I'm just moving the first instruction on top. This way, I don't need to flush this because I always know that this instruction is going to be executed in future. All right, so the compiler can move things around such that that instruction is always there. So I don't need to flush. Even if I see that I make a mistake with my branch, all I need to do is just updating my PC plus, I just update my PC and move on. I don't need to flush, okay? Because this instruction is here and I'm good to go. It's not easy. This instruction needs to be independent from the other instructions and all that. But if it is, and the compiler decides that this instruction is movable, it moves it to that delay slot. Just keep that in mind, okay? So this is actually quite common in many of this, because the nice thing about this is that now you're not at the mercy of the accuracy of the branch predictor. If you detect it correctly, great. If you didn't detect it correctly, you still do some useful activity there. All you need to do is just updating your PC and move on. Yes. You need to also change the microarchitecture as well. So the question is, how do you tell the PC not to flush that instruction? So again, there will be some flags from the compiler that this is not flushable or is flushable. Yeah.
Whether not doesn't rely on things that
Yes, so the compiler has that knowledge. So the compiler, first of all, knows the control flow graph, so knows when things are diverging and converging, and also compiler can understand the notion of dependency. So those things are understandable by the compiler. Yeah. Yeah, so it could generate data hazard. That's what I'm saying, that it also has to check the dependencies, right? So it has to be not dependent and movable, then you move it. So it's not guaranteed. Okay, last thing is that the compiler can do this thing called loop unrolling. Loop unrolling means that I can somehow reduce my branches, right? So for example, consider a for loop that I kind of like have a branch here and I jump back here. What I can do is that if I just copy this code twice or multiple times, I can reduce this branch, right? Because I can just run this and continue running it, because I can just increase the size of the code and repeat the same sequence of instruction multiple times. Loop unrolling will help me with branch misprediction. So if I want to really optimize my performance, I increase the size of my code. So basically I increase the instruction memory a little bit, but as a result of that, I no longer need to, like, the taken branch is basically gone, right? So you get benefit that way. So again, this is some performance optimizations that the compiler can do. There are a whole bunch of other things that the compiler can do. If you're interested, take a compiler course or read a book about compiler and you'll learn more about it. Unfortunately, we don't have time to go over them. Okay, so we understand how to reduce the miss penalty, but our branch accuracy is terrible at the moment, right? it's for actual branches is only 30%. For all the instructions together is only 86%. Modern processors have branch predictors that are like 95, 98, 96, 97% accurate in regular benchmarks. In some other benchmarks, it's not. So how do we get there? So can we make this design better? So the first thing that comes to mind is, why don't we predict taken? Because if 30% of the time, so the branch is only not taken 30% of the time, it means that 70% of the time this branch is taken. So if I can somehow have a method to distinguish between branch instruction and not branch instruction and predict taken for the branch instructions, I'm going to significantly increase the accuracy of my design. Okay? So what do we need to predict taken? And the reason that we didn't start with taken is that taken is slightly more complicated. Why? Because for taken, you need the address that you're jumping to as well. It's not just not taken, boom, continue. You need to actually know exactly where you're jumping to and fetch the instruction the next instruction exactly right after that you detect that this is a branch. So during your fetch stage, you need to know the new address. So that introduces new complexity, right? So essentially what you need to know is that now your next PC needs to be known during the fetch state, right? Why? Again, if I have a branch equal and I have my fetch and, if I do like, fetch and then decode, remember I told you that essentially this would be my I1 and I1 would be fetch here, and I make a wrong decision and boom, I can just get rid of this and continue. Now, if I actually make this branch taken, when I see the branches, when I see that this is a branch instruction at the decode stage, now I need to know what instructions am I fetching, right? And for that, I need my next PC known and updated right at the point that the branch equal is at the decode stage. In other words, in the next cycle, when the branch is in the decode stage, in the next cycle, I need my next PC updated, and I don't have that, right? Our design is just PC plus 4. At this point, the only thing that we know is the value of PC plus 4. That's why we go with not taken, okay? So let's see, can we somehow also predict my next PC during the fetch state? Okay, so examples that I just showed you. So this is the idea that we're going to go after. We're going to basically keep track of the history and the past. And using this history and the past, we're basically going to know that the next PC is going to be that. The first time I see a branch, I have no idea. I can basically predict not taken. But the next time I see that branch, I'm going to predict taken because I see that branch before. Okay, so how do we actually do that? So we're gonna basically use this idea called branch target buffers or BTBs, okay? So the BTB is this, that I have a table, okay? And this table basically remembers the branch and remember the address that it jumped to, okay? The first time this table is empty, right? I haven't seen any branch. I don't know any target address. I see a branch. I haven't seen it. I'm going to predict not taken and had the same strategy that I had before. But what I'm going to do is that as soon as I see a branch, I'm going to remember the target address of this branch. Next time I see that branch, I'm going to go into that table and say, aha, I saw that branch. Here was the address. I'm going to use that address. And now all of a sudden I have my next PC. Okay. So the question is how frequent this is. And is this always correct? So these are the two questions that we need to answer. That am I going to see lots of branches many, many times? That is there any sort of a recurrence happening in the branches? And then what if I actually make an incorrect decision? Are all the branches always jump to the same address? So if I just remember one thing, would that be okay? And would that be sufficient? We're going to answer these questions. Was that our questions, or you had a different question? Yes, it's very useful for loops, for example, right? Because loops, you always go back and many, many times. But maybe for functions, maybe not a great idea. For returns, maybe not a great idea. You see a PC, yes, yeah. So each instruction is tagged by a PC, right? So you know exactly which instruction is which because PC is kind of a unique identifier of each of the instructions. PC's targets, yes. Okay, this is what we call a branch target buffer or BTB. Okay, basically what BTB does, think about it as this table that has two columns. The first column is PC because PC is the unique identifier of that instruction. And the second column is the target address. Okay, so why do we use PC? We just spoke, we just explained it that PC is basically unique for each instruction. And then how big this table should be. In fact, the table doesn't need to be that big. Why? I'm going to show you later of why this does not need to be big. Just table that thing for a moment. Let me actually just show you the algorithm that I just explained. So the algorithm for a BTB is the following. We see a new PC, we record the target address in that table. So you use the PC as the index, and we record that address in that table. Next time that we see the same PC, we look at that table. If we see that there is a match between the PC and the PC recorded, we take the target address, and that is your next PC. So you don't do PC plus 4 anymore. You replace that PC plus 4 with the target PC that you have. Okay? So this would be basically the change in your fetch state. So remember in the fetch state, you had PC directly connected to the instruction memory. Now I'm introducing a new table called a BTB table. The PC also indexed into that. The output of the BTB is basically the new PC. And as you can see now, I put a mux here that it's either PC plus 4 or that PC is coming from that instruction, right? What is the criteria of deciding which one? It depends on whether I had that instruction within that BTB or not, okay? And all of these things happen in the fetch state, okay? So that's the difference. The fundamental difference that we are looking at here is that all of these things are happening in the fetch state, okay? Okay, so let's actually go back to the timing of this. So remember I had a BEQ and I said fetch and decode, and now I need to have this target instruction, and this target instruction is in the fetch state, right? So now I need to make sure the mechanism is actually working correctly, right? So once I decode the branch instruction, I need to somehow look into this table and kind of update my PC, right? So two questions. How do we know that this is a control flow instruction, right? So how do we know that I need to basically take this branch, right? Because I only take this if the previous instruction is a branch equal instruction, right? And the second thing is who updates the BTB? Like who actually put things in the BTB? What is the mechanism of where that target address is even known and how we actually update the BTB? I'm going to answer the second question first. So when do we update the BTB is when we decode the instruction. Remember I told you that I have PC plus offset and I know the direction of the branch during the decode stage, right? So I take that, whenever I see that, I basically go to the BTB and say that, okay, this is a new branch instruction and this is the target for that branch instruction, okay? So basically there's going to be, so if this is your decode stage, there's going to be kind of a feedback from here to here that writes to this BTB whenever we see a branch instruction and we know the target address of that branch instruction, okay? So that's an important thing. And we only write to this table when we know for sure that that is a branch instruction. We don't write to this table for all the other instructions, okay? So the nice thing about that is that also automatically answered the first question. Why? Because if there is a match in that table, it is guaranteed that that is a control flow instructions, because the entries in that table is only there when we have a branch instruction. So for every single instruction, I'm gonna do the following. If this is an add instruction, for example, I'm gonna put the PC and get the add instruction. I'm gonna also put the PC of the add to the BTB. It is guaranteed that the PC of add is not on that table. Why? Because the table is initially empty, and I only put the relevant PC from the branch instruction in that table. So I don't need to be worried about misprediction here, because I never put non-branch instruction in that table. I can just basically always, all the time, compare it with that table for all the instructions. It is guaranteed that only branch instructions are there. Okay, so there will be always a miss when we are searching that table for non-branch instructions. Okay, so in order to know that, okay, do I need to take PC plus 4 or do I need to take the next PC from that table? The answer is, if it's a hit from that table, take that address. If it's not hit from that table, do PC plus 4. Yes.
How does the search take immediate or it takes like some time?
The search. So the question is, how does the search happens in that table? The search is immediate. I'm gonna actually show you the circuitry for the searches. Yeah. You good? Any other question? Yes. Say it again. Mm-hmm. Yes. Yes. Yeah, yeah. So let's actually revisit the timeline, right? So let's say I have an add, a BEQ, and then an XOR, and then some other instructions, right? So the add instruction goes to fetch, right? So you go here. This is the PC for the add instruction. It goes here, and you have the add instruction here. The PC also goes to the BTB, and I said that it is guaranteed that it's going to be a miss, right? So immediately at this point, I know that my next PC is PC plus 4. Oops, what happens? Okay, I don't know what happened. My next PC is PC plus 4. Why? Because this table, there is no match for my add instruction. Okay, now I go to the next cycle. This add goes to the decode stage. Now my branch comes to this fetch state. Okay, two possibilities. Either I've seen this branch before. If I've seen this branch before, then it will be a match in that table. So the next instruction is not going to be this. It would be PC plus offset, whatever that PC plus offset is pointing at. So the next one, so this one goes to decode, this one goes to execute, and I'm not going to automatically fetch this instruction. I automatically have my PC plus offset. Whatever that instruction is, that would be my fetch. Okay? So far we are predicting only taken. So we always predict taken. Again, we might make a mistake, and we already have mechanism for predicting incorrect decisions. We flush, go back, and all that. Okay? But yes, it could be a branches that is not taken. Yeah, but it's taken the strategy for now. So we always predict taken. Yes, so if this is a hit, basically this one says go grab PC plus ops. Yeah. What happens if you haven't seen that branch is essentially it's like an add, right? So it's not a hit, you take PC plus 4. So first time predict not taken, afterwards predict taken. So when I say I always predict not taken, I lie, right? So it's most of the time you predict taken. First time you don't predict taken.
But then you score that like
Yes, when I see this, right? So if, for example, going back to this example, so I do fetch and decode and fetch. Here I don't see it. So I actually do fetch XOR here. But here I realized that, oh, this was a branch. So here I'm going to go back and update the BTB. It's too late for XOR, so XOR is fetched, but the next time it's not going to be fetched. Great. Let's continue. So as I said, nice thing about this is that this is guaranteed. Okay, so a quick recap. We reduce the miss penalty to 1 cycle by moving things to the decode stage, and we do always not taken, right? Always not taken was 30% accurate on branches, so we flipped this. So we say that, okay, let's predict taken all the time. To predict taken all the time, we need our next PC, the fetch state. That's when we introduce the BTB concept, okay? Again, that doesn't mean that we are perfect all the time. We only, on average, we are accurate 70% of the time. Still 30% of the time, we need to do the flushing and all that, but it's an improvement, okay? All right, so kind of like to break this down for you, for all the instructions, as you can see, for non-branch instructions, predicting taken is not a problem because the instruction is not in the BTB, so we are good to go. For branches, for those that are seen before, we will predict taken. For branches that we haven't seen before, we're going to predict still not taken. So keep that in mind, that it's kind of like, it's a dual kind of behavior. Yes? Yeah, so BTB is great for things that are repeating behavior and the same behavior all the time. If your branch is dynamic, so sometimes it's taken and sometimes it's not taken, like an if then else, then yeah, BTB is not great. Okay, so remember I told you why this would be helpful? This would be helpful because there's two very important things also happens a lot in designs when you're writing software. It's called the principle of locality, okay? You have two kinds of locality. There is what we call spatial locality, and there's another thing that we call temporal locality. Temporal locality is that what you just did, it's very, very likely that you're going to do it again, okay? In fact, 95% of the time of execution of a program is in some form of a loop. Like straight line code is only 5% of the time that you spend on the program, which is kind of surprising. But if you actually go and look at all the codes that you've ever written and try to profile it, you will see that 95% of the time you're either in some form of a for loop or a while loop, and only 5% of the time you're outside it. So that's why temporal locality is very, very, very common in all the workloads that you use, okay? The second thing is spatial locality. What spatial locality means is that if you do things, one thing, it's very likely you're going to do the surrounding of that, okay? For example, about data, this is very likely that if you bring A1, it's going to be very likely that soon you're going to bring A2 and A3 and A4 and so on and so forth. Same for PC. If I read PC equal to 100, very likely I'm going to be around that PC, right? Unless there is a jump and then I'm going to jump over. So there's going to be a big gap. But again, I'm going to spend a lot of time around that new PC, okay? So just keep that in mind. And that's why, so actually, the stats was 90%, so not 95%. So 90% of your time is in some form of a loop, okay? So this is the way that we're going to address the BTB then, okay? So basically, in order to address your BTB, you don't need your entire PC, because if you need your entire PC, then you need a massive BTB, right? So what you would do is that you take the first lower bits of the PC and use that to address the BTB. Why lower bits? Because lower bits gives you spatial locality. That if I'm, like, for example, looking at 100, then I want to also be able to distinguish between 100 and 104. But I don't care much about 100 and 1 million, because these likely not going to be close to each other, okay? So that's why the higher bits, there might be overlap, lower bits, I'll make sure that there is no overlap. And as you can see, I'm not using the first 2 bits. Why? Because first 2 bits is always 0, right? Like we always do +4, +4, +4. There's no point of using those first 2 bits. So I'm starting from bit number 2 and then use this thing called BTB index. The size of the number of bits is basically depends on how many rows I have in my BTB. And then I'm addressing my BTB that way. What is stored within each entry of BTB? It's a PC, it's a 32-bit number, okay? So I'm storing a 32-bit number or whatever the size of my PC is, I'm storing it in one entry of that, okay? And then I basically feed this as that this is the mux that goes back to the PC, okay? How do we compare the PCs? So essentially we use this tag table, right? So how do we know that this is a match, right? Someone asked that, how do you know that this is a match? So there are 2 ways that you can do it. Either you can store the PC itself here. So you get this n bit, you also store the n bit here. You compare these 2 guys. If there's a match, then you can address that, right? Or you can actually, if you have the entire PC stored, right? You can basically you can only store this part as the tag, and this part is already indexed into the table, right? So for example, let's say I have a 32-bit value, right? I use the first 10 bits to index the data, right? So I use this first 10 bits to index the table. What I need to store is I only store the rest of the 22 bits as the tag because I can always generate the full PC by doing the tag plus the index, right? I concatenate the tag plus index and I have my 32 bits. So either I can store the entire 32 bit if I want to, but the first 10 bits is already used for index. So there's no need to store that as well. I already know the index. So I can always concatenate these 2. So just the optimization that we make to make the tag storage smaller. But generally, it doesn't matter whether you do this that way or this way. You can always store the entire PC as a tag. So you get the PC, you have the current PC, compare these 2 bitwise. If it's a match, then it's a hit. If it's not a match, it's not a hit. Or you can store the remaining bits. So how many bits you are using for index, you store the remaining bits here, and then you concatenate this bits, and again, you have your full PC. Then you do the comparison. Either way, you're going to have the 32-bit comparison, okay? So this is basically what we are doing, right? So we have what we call a tag table, and we have a BTB. BTB is where you actually store the target PC, target address. It's 32-bit. Here, it could be 32-bit, or it could be 32 minus the number of index bits. As I said, either of these 2 are okay. Then what you do is that you compare this, the entire PC, with this value you store here. If it's true, then you select this address. If it's not true, you select PC plus 4. Okay? So this would be basically the entire logic that you need. The PC comes, okay? PC comes, you index the PC to the table, you bring in the tag, you compare the PC tag with this tag that you stored. If it's a match, then this value would be equal to 1, which means that this multiplexer will be selecting this value here. This value is your target PC. So your next PC becomes target PC. If this value is not a match, this will be equal to 0, which means that you're selecting PC plus 4. Okay? This is how this will work. Yes.
Yes. But I just also but it does seem possible that there could be case when I bought and this for these shows.
Yeah.
Or yeah, they're same, but then the top bits are different.
Yes.
So is there like
Yeah. Yeah, it is possible. So when I'm indexing lower bits, there is a chance of what we call a collision, right? So essentially, this method cannot distinguish between a scenario where all of these bits are 0 versus a scenario that, let's say, the first bit is not 0, right? For this, both of them are stored here, okay? But remember that I'm storing the entire tag of entire PC in that table, right? So what I'm storing here is the entire 32-bit. So I'm indexing to the same place, but the tags won't match. Okay? When the tag doesn't match, I'm not gonna take the branch. So it's like the branch would be not taken. Okay? Yeah. Good question. So the question is that if you've already seen this one with the index, you store that in the table, right? And now I'm saying that if a new branch comes that happens to be like this, same index, different tab, what will happen? So for now, just imagine one entry per row, okay? So they basically replace each other. So the 00011 would basically replace the one with all zeros. Later on, we're going to introduce other types of multiple entry, tables. There you can then store all of them at the same time. When we were talking about caching, you're going to see that a lot. For now, one entry per table. So if there is another one comes that has a mismatch, basically you kick this one out and you replace it with that one. And again, remember temporal locality. If I'm using the 000, likely I'm going to reuse that 000 in future. If I'm using 001, likely that I'm going to use that in future. That's why this will actually produce correct result most of the time. Okay? Yeah. Lower bits of PC. All of the bits, yes. But as I said, technically you don't need to store all the bits. You can only store 32 minus the index bit because you can always concatenate the index bit with that. But yeah, to make things simpler, assume that it's the entire 32. Okay? So as I said, this is kind of like the improvement. So I don't need to store the entire thing. I can store 32 minus index minus 2. Why minus 2? Because these two bits are also redundant to store. Okay? So if I want to really optimize this, this would be 32 minus index minus 2 instead of 32. But it could be also 32. Okay? So this would be how your fetch state look like now, okay? So you will have your BTB basically sends a control signal, and there will be an update coming from the decode stage as well, okay? We good? All right, so that's where we're gonna stop today. On Tuesday, I'm gonna quickly go over like the dynamic branch prediction as well, and then we're gonna do a review of all the things, okay?